A paper towel works because tiny spaces between fibers pull liquid into the sheet. The finished roll begins as a fragile wet web that can tear long before it feels strong. Creping transforms a flat, dried sheet into the bulkier, flexible structure associated with tissue products. Converting machines create the pattern, tear lines, roll length, and final household format. Paper towels turn a messy cleaning job into something fast, disposable, and convenient. The same product also supports restaurants and workplaces, where quick cleanup keeps routines moving.
One everyday roll can serve homes, schools, offices, kitchens, workshops, and countless cleanup tasks. That convenience depends on forestry, fiber science, water management, paper making, converting, and logistics.
Factories measure strength and absorbency because a towel that tears too early wastes product and effort. Sensors watch continuously, but operators decide when a change is normal and when it needs action.
Reliable production depends on maintenance work that is almost invisible when everything runs correctly. We will follow the full chain, from fiber source to the moment a finished roll reaches daily life.
Paper fiber begins with trees, but responsible supply chains manage forests as long-term renewable resources.
Planning matters because fiber quality, harvest timing, access, and future regrowth begin before cutting.
Mechanized harvesting processes timber efficiently while keeping workers away from the cutting head. Moving logs on a forwarder reduces unnecessary ground contact before transport to the pulp mill. Sorting creates a predictable raw material stream before trucks begin the next stage.
Transport links forests to mills, so stable loading matters as much as harvesting speed.
At the mill, the first job is verifying what arrived and directing it into the correct stream.
A wood yard buffers supply, so the mill does not depend on one truck arriving at exactly the right time.
Removing bark protects pulp quality and creates a separate material stream for recovery or energy.
The chipper reduces large logs into pieces that can be processed more uniformly during pulping.
Uniform chips help heat and pulping chemistry reach the wood more consistently. Screening narrows chip size because very large and very small pieces cook differently.
Oversized pieces are reduced again before rejoining the usable chip stream. Storage smooths the difference between irregular truck deliveries and continuous mill demand.
Sampling reveals whether wood preparation is giving the pulp mill a stable feed.
Now the material stops looking like timber and begins transforming into individual fibers.
Pulping separates useful cellulose fibers from much of the lignin holding the wood structure together. Inside the digester, controlled chemistry, temperature, and residence time work together on the chips. Operators rely on measured process conditions and verified fiber results, not just visual judgment. After cooking, rigid chips become a wet mass of separated fibers and dissolved wood components. Washing separates dissolved material and supports recovery of process chemicals from the fiber stream. Chemical recovery is one reason pulp mills operate as integrated process systems rather than simple grinders.
Screening protects downstream equipment and keeps unwanted particles away from the tissue machine. Different cleaning stages target different contaminants because no single separator removes everything well. Quality checks turn a flowing process into evidence that the fiber is clean enough to move forward.
Additional treatment can reduce remaining lignin before brightness stages for selected products. Brightness stages are controlled carefully because tissue performance depends on fiber quality, not color alone.
By this point, the original wood is unrecognizable, but the cellulose fibers remain intact.
Final screening protects appearance and runnability when fibers reach high-speed papermaking equipment. Storage lets the pulp mill supply steady fiber even when upstream operations fluctuate slightly. An integrated site can move wet pulp directly, while other tissue mills may receive dry market pulp bales.
Many tissue mills buy market pulp, so the fiber journey can continue after transportation as dry bales. Repulping turns dry market pulp back into a pumpable fiber suspension for stock preparation.
The goal is to redisperse fibers so they can move individually through the stock system.
Early screening protects pumps and refiners from material that does not belong in the furnish.
Consistency control matters because papermaking recipes are measured in fiber concentration, not just liquid volume.
Fiber is ready. The next challenge is balancing absorbency, strength, bulk, and cost. Some tissue grades use recovered fiber, but incoming paper must match the required product quality. Sorting starts before pulping because large contaminants are easier to remove while still visible.
Repulping uses water and agitation to separate old paper sheets back into reusable fibers.
Screens protect the process by removing materials that never become useful paper fiber.
Cleaning equipment uses physical differences such as density and size to separate contaminants from fiber.
When brightness matters, additional cleaning can remove inks, coatings, fillers, and other fine material. Recycling creates residual streams, so mills manage both recovered fiber and the contaminants remover from it.
Recovered fiber becomes useful when its quality is predictable enough for the grade being produced.
Different fiber sources behave differently, so blending decisions depend on the performance the towel needs.
Mills choose fiber blends according to product design, quality targets, and available supply. Longer and shorter fibers can contribute different properties, so mills control them separately. A paper towel recipe is partly a fiber recipe, balancing strength, formation, bulk, and feel. Refining changes fiber surfaces so they bond differently when the wet sheet forms and dries. Too little or too much refining can shift strength, drainage, and energy use across the machine. The blend chest gives separate fiber streams time to become one stable furnish.
Selected additives can support wet strength, dry strength, processing, or other grade-specific targets.
Before forming, the suspension becomes mostly water, so the fibers can spread into a uniform thin sheet. The approach flow system must deliver stable pressure because the head box converts flow stability into sheet uniformity. Final screening is the last defense against debris that could mark the sheet or break the fragile web. Even tiny particles matter when the finished product is only a few light layers. Air bubbles can disturb flow and formation, so stable papermaking often begins by removing invisible problems.
A rising pressure difference can signal that a screen is collecting more contaminants than normal.
Redundant equipment lets production continue while a dirty screen is removed from service safely.
Maintenance prevents a small restriction from becoming unstable flow or an unexpected production stop. The system is recovered only when measurements return to a stable operating range.
Fiber preparation is complete, and from here,
water removal becomes the main engineering challenge.
A tissue machine turns dilute suspension into continuous paper in seconds while controlling an extremely fragile web.
The headbox must spread fibers evenly because every later machine depends on the sheet it receives. Formation begins when water leaves through the fabric and fibers start locking into a continuous web. Vacuum drainage removes water efficiently while the web is still too weak for ordinary handling. In a short distance, dispersed fibers become a sheet that can finally be transferred onward. Transfers must match speed and tension because even a small mismatch can tear the weak tissue web. Mechanical water removal saves drying energy, but too much pressure can reduce useful sheet bulk. The sheet must attach evenly so drying and later creping remain stable across the full width.
The Yankee is a large steam-heated cylinder that supplies a major part of the drying energy. The hood adds drying capacity, while ventilation carries evaporated water away from the sheet.
A moving scanner checks the moisture profile so operators can see whether one side dries differently. A wet edge can change creping, strength, and winding even when average moisture still looks normal.
Small controlled adjustments correct the profile without forcing the whole machine into a large change. Correction succeeds when the full width becomes stable again, not just one average number. At the creping blade, the sheet compresses into fine folds that increase bulk and flexibility.
Creping changes structure, which is why tissue feels very different from ordinary writing paper. Careful tension control keeps the lighter, bulkier web from becoming unstable after creping.
The paper machine does not make kitchen-size rolls directly. It first creates enormous parent reels. A stable parent reel protects the web from wrinkles and makes converting easier downstream.
Reel changes turn continuous papermaking into discrete giant rolls that can move to converting.
Mechanical handling is essential because parent reels are far too large for ordinary manual movement. Basis weight tells the mill how much fiber is present per unit area of sheet. Strength testing shows whether the towel can survive handling before and during a real cleanup job. Absorbency is tested directly because thickness alone does not guarantee good liquid uptake. Caliper helps describe bulk, but useful performance comes from structure and fiber bonding together.
A giant roll becomes usable inventory only when process data and product measurements agree. The creping blade is a wear part, so planned maintenance is better than waiting for quality to drift. Blade condition affects crep quality, making controlled replacement part of product consistency. Maintenance ends only after alignment, guarding, and safe restart checks are complete. A successful restart proves maintenance restored both machine condition and sheet quality. Converting changes industrial-sized tissue reels into the roll format that people recognize at home. Tension control keeps a light web flat enough for embossing, perforation, and rewinding.
Many kitchen towels combine plies to balance strength, thickness, and absorbency.
Ply alignment matters because mismatched layers create wrinkles and weak edges in the finished roll.
Embossing creates texture and can add bulk while helping multiple plies work together. The raised pattern creates structure that can help hold liquid between fibers and layers. Perforations let people tear one sheet at a time without scissors or wasting a long strip. Edge sensors keep the sheet centered because alignment errors become obvious after thousands of rotations.
Even the cardboard core is engineered to stay light while remaining strong enough for winding and shipping. Core length must match roll width, so edges stay neat during high-speed winding. The rewinder creates one long paper towel log containing many future household rolls.
Diameter control keeps package size consistent and prevents one roll from quietly consuming excess material. Accumulation separates winding speed from cutting speed, so a short pause does not stop everything. The log saw turns one long cylinder into many identical kitchen rolls in rapid sequence. Cut quality matters because crushed or uneven edges make rolls harder to package and dispense. A distorted edge can reveal a tension problem even when the tissue itself is perfectly good.
The visible roll defect points backward to the part of the line that needs attention. Small converting adjustments can prevent one alignment problem from repeating across hundreds of rolls. The line returns to normal only after new rolls prove the tension problem is gone. Mounting converts a continuous production stream into the exact pack configuration sold to consumers.
Primary packaging keeps clean rolls together and protects them from dirt and moisture during distribution.
A secure package prevents rolls from separating before they reach warehouse or store. Finished inspection confirms converting created the number, size, and format required by the product specification.
Absorbency depends on fiber structure, sheet bulk, bonding, and converting design, rather than appearance alone. Wet strength matters because a towel is most useful when it stays together after contacting liquid.
At microscopic scale, absorbency comes from spaces between fibers that draw and hold liquid.
Papermaking moves large water volumes, so mills recover and reuse process water where system design allows. Recovering lost fiber reduces waste while keeping more solids out of wastewater treatment.
Water leaving production still needs treatment before discharge or further reuse.
Good preparation creates side streams that can support energy recovery or other useful applications. Clean mill broke is valuable because its fibers can often return directly to papermaking. Secondary cases protect light, bulky rolls and make warehouse handling more reliable. Robots fit repetitive palletizing because cases arrive in predictable shapes and sequences.
Load stability matters because crushed cases can deform rolls before a consumer sees them.
Paper towels need no refrigeration, but they still need dry storage and physical protection.
The final logistics challenge is moving bulky, lightweight products efficiently without damaging them.
A process spanning forests, water, steam sensors, and giant reels ends as an ordinary shelf item. The everyday payoff is simple. Controlled fiber structure becomes a tool that saves cleanup time. Using only the amount needed is the simplest way to reduce material use without changing the product. Disposable sheet connects forestry, chemistry, mechanics, automation, maintenance, logistics, and household behavior.
Once you see the chain, a paper towel becomes more than a simple white sheet.
Product works because fiber, bulk, bonding, and converting are designed to perform together.
Everyday products surround us, yet each one hides a different combination of materials and engineering.
Process ends here, but the next product begins with a completely different raw material and system. The next ordinary object may be even more surprising
once we follow its full journey.